This week's lab section will focus on biodiversity, more specifically population densities, abundance and diversity, species richness, evenness, and sampling strategies, the Shannon-Weiner index, and some other basic mathematical and statistical concepts. Don't worry though, the math and stats bits are for more conceptual understandings in how to monitor and measure biological diversity. When assessing a population, we have to pay close attention to the scale, or the size of our population and the size of our sample. But how do we determine what sample size to use and where and how to take these samples? It makes sense that there's some relationship between the size of our area sampled and the number of samples that we take. If our samples are large, for example, we might only need to take a few samples. However, if our samples are small, we might think that we would have to take more in order to compensate. And to further complicate things, we need to sample rare species and species that are clumped together, like oysters that aggregate together. What a mess, right? Now this next section might be a little bit confusing. So the number of samples we take may seem to be related to how much variability there is from one sample to another. If variability among samples is low, then we may get similar results in all of our samples, resulting in a lot of samples, let's say. However, if variability is high, or we get a vastly different number of results from sample to sample, then we need to take a higher number of samples. So how do we measure variability? We can do this by calculating a mean with a standard deviation or an SD. Don't worry though, we're not going to expect you to calculate standard deviation by hand. Most statistical software tends to do this, but I'll write it on the board for you anyway. The important take-home message is that a larger standard deviation means that there's more variability than a smaller standard deviation. So if we take 3 examples and calculate a mean and standard deviation of the 3, and then take a 4th sample and calculate a mean and standard deviation, take a 5th, etc., we would see a progressive decline in the overall standard deviation. And after taking more and more samples, however, the standard deviation may change little, which would represent that the true variability of the population is now being represented. So measuring density is relatively straightforward with just the counting data. The tricky part is measuring diversity. Here there are 2 things to consider. One is species richness, or the number of different species that are present in a particular area. This is easy enough to extract from our counting data by determining the density of different species. The second tricky thing to consider is species evenness. This has to do with the relative proportions within each species that we encounter in an area. So think of this example. We have 100 individuals. We find that there are 10 species within, and 10 animals within each species. We're going to see 100 total individuals. And if we see that species richness is also 10, we would expect that the species evenness reflects the overall distribution within the population. If we sample another 100 individuals from a different site, see that there are, for example, 84 individuals of species 1, 8 of species 2, 1 of 3, 1 of 4, and so on until 8. We're going to get another 100 overall individuals. But clearly the community is then dominated by species 1, and the overall evenness of site 2 is low. Question for you. With those examples in mind, which extreme would you expect to represent a more stressed community? Right, the second example with 84 individuals of species 1 is more stressed because the evenness is low and there's only one species that dominates the overall environment. Now do you see how diversity is dependent on richness and evenness? But how do we determine the index of the diversity? Well, there are several indices, but we need to realize that whichever one we use, it's only a relative index, or relative to the community that we observe. The actual numbers that we calculate here have real little meaning. Having said that, one index that's been traditionally used to measure diversity is the Shannon-Weiner index. This index takes both species richness and species evenness into account. In this equation, H is the Shannon-Weiner index, P subscript I is the proportion of species, I, in your sample, and ln of P subscript I is the natural logarithm of the proportions of species I. Okay. Let's look at the examples of 100 individuals. We found 10 species and 10 animals per species. The proportion of individuals of each of the species is the same, or 0.1. So here, H equals -1 times 0.1 natural log minus 0.1. So H equals -1 times 0.1 times ln of 0.1 times 10, which equals 2.3, or H equals 1 times 0.1 times minus 2.3 times 10, which gives you the same value of 2.3. In the second example given, the proportion of species number 1 is 0.84, i.e. 84 individuals with species 1. That of species 2 is 0.08, and that of the other 8 species is 0.01. So the Shannon-Weiner index here, H, equals minus 1, bracket, parentheses, 0.84, times minus 0.17, plus 0.08, times minus 2.53, plus 8 times 0.01, times minus 4.61, giving us 0.71. By comparing the H values, you can determine if diversity is greater or lesser at a site where you've sampled, or whether one sampling regime reflects greater diversity than the other one. In this case, the Shannon-Weiner index shows that therefore the diversity is much higher for the first example than the second, and the index can be easily calculated after setting up your data in an Excel spreadsheet later in the lab.